In this video, I'm going to show you guys how to predict either the pressure of the atmosphere outside the manometer or the pressure of a gas inside a container on the other side of the manometer. In the first problem on the left, it wants you to predict the pressure of the gas inside the container. So I often like to label the drawings so that I can keep straight which gas or which atmosphere we're solving for pressure. So in this case, I'm going to put a question mark on the gas container so I know that that's what I'm solving for. And it goes on to say I want that pressure solved in millimeters of mercury. And the atmosphere pressure is 103.8 kPa. Now, before I can even deal with the rest of the problem, I have to realize that the height of the mercury is noted as 7 millimeters of mercury. And in order for us to use our guide mathematical relationship for pressure of the unknown, which in this case the unknown sample is going to be the gas, in order to find the pressure of the unknown gas, we have to take the pressure of the known sample, which in this case is the atmosphere, and we have to decide whether to add it or subtract it with the change in height. And in order to decide that, you have to conceptually think about who has more pressure or force pushing on the mercury to hold up that mercury column. But we can't even use this equation until we get the units into the same family of units, because during addition and subtraction, you have to have the families of units in the same family. And since the directions say I want it in millimeters mercury, I'm actually going to change the atmospheric pressure from kPa to millimeters of mercury. So that means I have to do a unit multiplier. Starting with what I have, I'm going to take it times a known ratio. And this known ratio that I'm going to multiply it by here is just built from the standard pressures listed in class. So I know that the standard pressure in kPa is 101.3 kPa. And to make the jump to millimeters of mercury, I know the standard pressure millimeters of mercury is 760 millimeters of mercury. The kPa units cancel out, and now you can do the mathematical work across the top. So make sure you multiply the 103.8 times the 760 across the top. Do not take the 103.8 times the bottom denominator. So if you take 103.8 times 760, you should get approximately 78,888 millimeters of mercury. And don't forget to bring down the 101.3 that's still left over. And if you simplify that, you should get a pressure for the atmosphere to be 778.8 millimeters of mercury. Now the pressure of the atmosphere is in millimeters of mercury, and so is the height change at 7 millimeters of mercury. So now we got to conceptually decide if we're going to add those two or subtract them. And you have to go over and mark on your manometer if the atmosphere side is under more pressure or less pressure. Most students will tell me that the atmosphere is under more pressure. I don't want you guys simply to say because the level of the mercury is lower. I want you to conceptually think that if they were equal pressure on both sides, the levels would be equal. So the atmosphere must be applying more force to the surface of this mercury down here and shoving it up and over. So really the atmosphere is holding up the weight of all this mercury that got changed for its height. So the atmosphere has more pressure than the gas. So that tells me in order to find out what the gas is, I have to take the atmosphere pressure and subtract the height change that it goes through. Atmosphere pressure was 778.9 millimeters of mercury. I'm going to subtract the 7 millimeters of mercury height change. And when you do that, you should get the pressure of the gas is equal to 771.8 millimeters of mercury. Now you can check to see if this makes sense. Standard pressure is 760 millimeters of mercury, but we started off with the atmosphere at 778.9 millimeters of mercury, and so this one is 771.8, so that's less. The pressure of the gas is less than what we calculated for the atmospheric pressure, which matches up with the visual aid of the drawing. The gas cannot compete with the atmospheric pressure with the mercury being shoved up and lifted up and the weight held by the atmosphere. So it makes sense that the 771.8 millimeters of mercury is less than the atmospheric pressure given in the directions. Now take a look at the problem on the right, and you can feel free to pause the video and try this one completely on your own before resuming. In this example, I want you guys to predict the pressure of the atmosphere this time. So I like to come over here and mark that this is the question mark side, and I want you to get that in PSI, otherwise known as pounds for every inch squared. If the gas in the container was 12.2 pounds for every inch squared, the height of the mercury is noted at 11 millimeters of mercury. So again, just conceptually identify which side's under more pressure. Since the liquid mercury is held up on the gas side of the container, then the gas side of the container is under less pressure also. So in this case, the atmosphere is greater again than the gas in this case. So I know that the atmosphere pressure needs to be larger than the gas pressure because it's applying a force to the surface of this mercury once again, and it's holding up this column of mercury which has a weight also. So somewhat of a similar example to the last problem, but it's different because of what we're solving for here. In this problem, we're predicting the pressure of the atmosphere. In the last problem, the atmosphere was given to us. But we're in the same situation. You cannot do our mathematical calculations without first getting the units into the same family. You cannot find out the pressure of the unknown by taking the pressure of the known gas plus or minus the height change until you get the height change and the pressure of the known in the same units. And in the directions it says it wants it in PSI, pounds for every square inch. So I'm going to change the height of the mercury actually in this one to PSI. If you guys look at the height, it's 11 millimeters of mercury. Now I need to do a unimultiplier and get a ratio to cancel those millimeters of mercury out. If I use the standard pressures given in class, I know that 760 millimeters of mercury is equivalent to 14.7 pounds for every square inch. And I've been flexible in class with how you write the pounds for every square inch. Some people will write the 14.7 pounds and then put it over 1 square inch, and that's how I often will do it. But when doing a unimultiplier, it's confusing with the 1 square inch being stuck in the bottom when really it's a ratio in the numerator of another known ratio. So I'm okay with you guys stacking the pounds and the inches squared kind of compacted up in the numerator. Millimeters of mercury cancel. If you multiply 11 times the 14.7 pounds for every inch squared, you guys should get something along the lines of 161.7 pounds for every inch squared. And remember, you got to bring that 760 over because you do not take the 11 and do not multiply it times the 760. You multiply straight across the top. And then if you take 161.7 divided by that 760, you guys should get a change in height or change in pressure of 0.21 pounds for every 1 inch squared. Now that I've got my change in height, or the change in pressure in pounds for every square inch, and my pressure of the gases in pounds per square inch, I can now make a decision conceptually about whether I'm adding or subtracting them to get the atmospheric pressure. So I know that the gas pressure given in the problem was 12.2 pounds for every inch squared. Now I got to decide if this was 12.2 over here, pounds for every square inch, and I want to get the atmosphere. I got to conceptually think, is the atmosphere going to be greater pressure or less pressure? And if you remember, we've already identified that the atmosphere must be applying more force on the area of mercury to shove up the weight column of that mercury, so it must be under more pressure. So the atmospheric pressure must be the atmosphere plus that height change, or excuse me, the gas plus that height change. So we're going to add on the 0.21 pounds for every inch squared. And now, since we have like terms of PSI, pounds for every square inch, we can add these up. And so what we should find is that the pressure of the atmosphere is approximately 12.41 pounds for every inch squared.